Everybody, welcome to my channel. Today we have a very good problem for you guys called product of array except self. Right, this is a very good one, so make sure you pay close attention to the problem statement. Right, so it says given an integer array nums, right, return an array answer such that the answer of I is equal to the product of all the elements of nums except nums of I. Right, so okay, the product of any prefix or suffix of nums, right, is guaranteed to fit in a 32-bit integer. Okay. You must write the algorithm in O of n, right, time, right, and without using the division operation. Okay, so pretty simple problem statement. So as you guys can see, they're telling us to return the for every index, right? We need to return the product of all the elements in nums, but not including the number at that particular index, right? That's kind of what this is. They're saying here, right? Okay. So for every index we calculate, right, we compute the product of all the elements in the array, but without including the nums of I in there, right? That number at that particular index, right? So the product of any, and they're also saying that it would fit into a 32-bit integer, right? So the product of any, so we don't have to worry about using long or whatever, right? So 32-bit should be fine. So we can't use division, right? So let's go through a couple examples so we can solidify the ask, right? The ask is always you can see 1, 2, 3, 4, pretty simple scenario, right? And as you can see, the product, right, of all the elements in the array, right, not including 1 for the first index, right, index 0. 2 times 3 is 6 times 4 is 24, so we have 24 here, guys, right? All right. You might probably saying, yeah, they multiply 1. No, they didn't multiply 1, right? For example, let's go to the index 1, right? So we have 2 here, right? So we multiply all the numbers, right? 1 times 3 is 3 times 4 is 12, right? So we have 12 here, guys, right? So as you can see, we don't include 2 in there, so we have 12 at this spot. And then we do the same thing for this one. 1 times 2 times 4 is 8. And then we do 1 times 2 times 3 is 6, right? For the last index, right? So, yeah, right? So, how could we solve this problem, right? The straightforward approach, right, would have been to just multiply everything together, right? And then go back and divide, right? So for each index, so let's say we get 24, right? We do 24 divided by 1 is 24, okay? 24 divided by 2 is 12, right? So the division would practically remove that element, right? From the total product that we have, right? So that's kind of what the division would be, right? But instead we could use the division, right? If we could use division, it would have been as straightforward as that, right? We just get one product and then we just go and do a loop and remove each element from the total product, right? And then return that answer, right, for every index, right? But that's not gonna work out, so we have to be a little bit more clever than that, right? So how do we be more clever, guys, right? That's kind of what the thing is. So what I'm thinking straightforward, right? Solution. We normally love to start with straightforward solution, right? To maybe we could do for every index, right? Multiply, right? All the products in the array, right? But we skip whatever element that we're on, right? So it would be like, we need a linear loop to loop through the array, and for each index, I have another linear loop to scan the array, right? And calculate all the product of all the elements in the array, but except not including that element, right? So for 1, we would be at the first index, right? And then we would go to, and then the other loop will start at the beginning of the array, right? And then start calculating, right? So we'll skip index 0 because we're, right? Then we go 2, 3, 4, right? Get 24, put it there, and then we go out, and then the first for loop goes on to the next one and next index, right? And then, we have 2 now. So we calculate all the numbers, right? So 1, we skip this index, and then we go 3, 4, right? And then we see that equals 12, we put it there. So we'll do this for every index, right? Double for loop, straightforward, that's, not too good, right? As you can already tell, right? This n squared solution is not too good, right? Even though we're not using space, we're efficient in space, but the time complexity is not too impressive at all, right? So what can we do to kind of have a more impressive time complexity, right? I'm saying to reduce the time complexity a little bit, right? You know what I'm saying? And log n, and how do we bring it down? Because n squared is too much, right? So what I'm thinking, right? So I can show you guys so this is how the code would look like, right? For the n squared solution, right? Double for loop, so linear loop, 2 loop, 3 array for every index. We compute, right, the product of all the numbers, right? So we use product of 1, right, because it doesn't affect anything using 1, right? And then we just multiply, product of all the elements in there, right? And once we do that, we just put at that particular index, right, put the product of all the elements, right, not including, right? It doesn't include the element at that index because we're skipping it pretty much, right? So if I is not equal to j, then we do it, right? Okay. So yeah, that's how it would look like, right? So how can we improve, guys? So we do a lot of repeated work, as you can already see from the example that I gave you guys, right? We're recomputing, we're going over the array over and over again, right? And we normally know that when we need to reduce the time complexities, we normally introduce some sort of a data structure to kind of help us to reduce it, right? Maybe caching some information instead of doing things repeatedly, right? Normally it helps us to bring down the time complexity. So so that's exactly the type of thing that we do, right? So what kind of information do we need, right? So for every index, right, thing that could be useful is because we can't use division, right? We can't just multiply everything and then divide, right? That doesn't work. So we need to be more clever. So what I'm thinking is we could store information of the product, right, of all the elements to my left, right, and the product of all the elements to my right, right? So let's say for 2, right, if I somehow knew the product, right, of all the elements to my right, right, and the product of all the elements to my left, right, not including myself in there, obviously, then I could just multiply that together, right, and we'll get my result, right? So for index 1, right, you see we have 2. The product of all the elements to its left, right, is 1, right? And the product of all the elements to its right is 12, right? So we just multiply 12 times 1, and we get our answer 12, right? You can do this for every index if you think about it, right? So for index 2, we have 3, right? So the product of all the elements to my left is 2, right? And the product of all the elements to my right is 4, right? And so we're able to get 8, right? So if only I was able to get the information, I would be able to easily solve this, right, of n, right, without having to keep looping, right? So we would need to do some sort of a pre-processing. I'm thinking about. We can calculate, right, for each index, right, the product of all the elements to its left, right, and the product of all the elements to its right, right, and then I multiply those two things together, right, because I have that piece of information, right. I only need to, because hopefully I can build those piece of information of n, right? So the time complexity can be low, right? And then we would be good, right? Just multiply that information and we'd be good. So so how do we build that information, right? It's kind of what you're probably asking now. So we build it in a way that so the same concept as we did something similar to that, right? The running sum, or right? But this one will be like a running product for each index, right? So we would start off, with so this is, for example, let's say we have this one, right? Just do it quickly. Zoom in. I think this is a lot better. So we have something like that, right? So the running sum, so there's an edge case. So if we say we're building the left side of things, right? So the left will be, since the first index doesn't have anything to its left, right? Then we use the default one, right? Because it won't affect anything, okay? And then now for index 1, right? We see that all the elements to its left, right, is 1, right? So we put 1, right? Okay. And also we do the same thing for this one, right? The product of all the elements to its left, right? So we get that information, right? So we know what's my previous, right? So we know the product of all the elements up to my previous index, right? Not including my previous index, right? Okay. So we actually just capture that, so it's 1, right? And also we include the element that's there, right? Because its left doesn't include, right? Its index, right? Doesn't include itself in there, right? So we need to multiply also by 2, right? By the previous index, the number of the previous index, right? So we have 2 here, and then but the last thing, right? We do the same thing, right? You ask so index 0, 1, 2, 3, right? So it's going to ask what's your previous, what's the product of all elements to your left, right? Okay. I have that information there, right? I don't need to recompute it. I could just use my previous index, like, data point, right? Okay, so it's like, all right, it's 2. Okay, cool. But also we need to include 3 in there, right? Because 3 is to this guy's left, right? Okay, so we need to include it in there, because if we just only use that, right, it wouldn't be accurate, because this guy, so the previous index includes all the elements to its left, not including itself, right? So when we go to the next index, we multiply by, so we get that information, right? So we get the previous index, the product of all the elements to its left, right? And also multiplying it by that number of the previous index as well, right? To include it, because from the index 3's perspective, 3 is also to its left, right? So that's why we have that. So it's also make sure it makes sense, right? So it will be 2 times 3 is 6, right? So that's how we will build it, right? And we will do something very similar to build the right side of things as well, right? Be kind of a similar concept, okay? So hopefully it makes sense, right? So let's go ahead with the code. The code will be very simple. Hopefully can clarify any doubts you may have, right? The comment section if it didn't make sense, right? So I can do better next time. Also, we get the length of the array, and then we have a left, right? So this is going to help us to build those pieces of information that we need. And then we do the same thing for the right. Okay. And then we just do a linear scan to build things, right? So remember the edge case that I told you about, right? Because there's nothing to the first index, right? Left the first index. So we put a 1, right? And then we go ahead and start our building the running product, right, for each element, right? So it will be 1, I is less than n, I plus plus. So it will be for left of I, right? Will be done by left of I minus 1, right? So I get that information, right? Times the nums of I minus 1, right? And I've already explained the reason why we do that, right? And then we do something very similar for the right side of things as well, right? But we're doing it in reverse, right? So n minus 1, so the last index, right? There's nothing to its right, right? So we put 1, okay? And then we loop backwards, right? I is equal to n minus 2, because we already took care of n minus 1, right? Then I is greater than or equal to 0, I minus, right? And then the right of I equals to same thing, I plus 1, right? Whatever the product it is, right? Times nums of I plus 1 as well, right? Similar concept, guys, right? We use it's the product of all elements to its right times that number itself, right? So the right pretty much helps us to build the running product for every index, right? It includes all the product of all the elements to its right? Not including itself, right? Okay. I think that we're good. We know we computed all those computation, right? So now what we need to do is simply just do an I equals 0, right? Just a linear loop, right, to build it. So let's capture things here. So we need the results as well. So res equal to int. Okay, so we have so res of I have the result of everything to my left, right? And I have the result of everything to my right, right? Okay. So for every index, for left, right, includes all the product of all the elements to its left, and the right includes the product of all elements to its right. We just go ahead and multiply right through, right? Because we have this information. We don't need to keep looping through to find that, right? Which was the bottleneck that we had earlier. And just like that, I think we are in good shape, right? Let's press run code, guys. See if everything was good. Press submit. See if that's all test cases. Awesome, guys. We're able to pass all the test cases, guys, right? So there's even a better solution than this one, right? Which is that we can just go ahead and build our, which I think it's worth mentioning, right? So we can build, so we can use one. We don't need to build like, we don't need a left and a right? So we could use the res, right? The result output to build the left side of things, right? So we compute the left side of things. So every index has the product of all the elements to its left, right? Once we have that, right? We should just throw it in there instead of using left, right? So we can even comment those out. Those are not needed anymore, right? Left is not needed anymore. So we store everything in the left side of things, right? Okay. So now for the right side of things, so how is it going to work, right? We could store, so we could dynamically build dynamically store the running product of all of the elements to its right, in one variable instead of storing for every index, right? So how it's going to work is going to be very intuitive. I want to show you guys, right? So we could comment those things out. I don't think we need that anymore. So let's right. So yeah, so we need to backward, right? So remove that. It's not needed. going on with my mouse? Okay, so now how it's gonna work out. So we're just gonna store, right? So originally we start off with everything, right equal to 1, right? Originally, because there's nothing to the last index, right? For 4, there's nothing to its right? Okay. So how's it gonna work out, right? So we build the left side of things, right? So this is what res will equal to now. Okay. And then we have this right variable that equal to 1, right? And then we are looping backwards, right? So so nums of I, right? Okay, so we do so the right variable. So instead of, see how we're doing, right, I plus 1, right, which is the previous, right, elements, right? It includes it includes that, right? So how would be for every I, right? It would be res of I, because we know so it includes the left side of things times the right variable, right? So originally, so right equal to 1, right? So we do 4, we do 6, right? Because 6 times 1, right, equals 6, right? So it stays 6, okay? All right, which is the answer we have here, right? And then now, right, for the next iteration, so when it goes to before it goes to the next index, right, we multiply it by whatever number that we're on right now, right? Because it would be included, right? Instead of doing this I plus 1, right, we just go ahead and dynamically add it to the right variable, right? So now, for this index, so it would be 1 times 4, right? Because 4 is everything to its right so far, right? So we have 4, and then we go ahead this one, and we do 2 times 4, because right now it's equal to 4, right? Then we have equal to 4, right? So we have 8, right? And then before we go to the other one, the other index, we multiply it, right? So now it's 4 times 3, right? Because 4 times 3, because that's the index that we're on, right? Okay. And then now is equal to 12. So we do 12 times, so it's like, so this index, right? 1 times 12 gives you 12. That's why we put 12 here. And then we do the same thing here. And then we multiply 12 times whatever number is that this index, right? Now it's 24. Right. Just like that, we are in good shape. We're able to solve this problem, guys, right? We get to this index, we multiply with whatever's there, right? Because whatever's there is everything to its left, right? And I know what everything's to my right because of the variable that I'm holding that's dynamically building it as we go along, right? That's kind of the improvement that we did. So now the time complexity went down, and we're pretty much in good shape. All right, press submit. All right, we're more efficient on space, So yeah, if it makes sense to you guys, in the comment section. If you're new here, make sure to subscribe because we'll be doing a lot of other videos just like this one. So I want to thank you guys for watching, and I'll see you guys in the next video.